Welcome to week 3 of our course. This is lecture 14. The topic is discrete valuation rings or DVRs. So this is week 3, lecture 14, and the topic this week is discrete valuation rings. Or DVRs in short. Okay, so and the goal of this week really is to give some examples of valuation rings, just some abstract concepts that we learned last week. Just recall, suppose you have this totally ordered abelian group. And just as an example, the simplest example of such a group is the ring of integers or the group of integers with the addition sign and the usual greater than equal to. This is an example of a totally ordered abelian group. And in fact, if you start with a totally ordered abelian group, any subgroup is also a totally ordered abelian group. So any subgroup gamma naught, say inside gamma, also gives as an example of a totally ordered abelian group. And we say that two totally ordered abelian groups are isomorphic. So let's call it gamma 1 with its own plus, its own addition and greater than equal to, along with another group gamma 2. So we say that they are isomorphic. If you have a group homomorphism with respect to plus 1 and plus 2, that is compatible with the respect to partial ordering, with the total ordering. What that means is that if you have element x that's larger than y, then if you apply this group homomorphism, that's larger, f of x is larger than f of y. Okay, and again recall we have this valuation function, so we say a function from the multiplicative group of the field, so k cross, every element in k except the 0 element is a valuation. It satisfies two properties. So if you take any x and y in k cross, then you have two properties, that the valuation of the product is v of x plus v of y, and if x plus y is not 0, then what we had is that you can take the valuation of the sum that's larger than equal to the minimum of v of x and v of y. So the first property is just saying that v is a group homomorphism. And the second property is what's called the ultrametric property. Okay, An observation is that, so since this function v is a group homomorphism, since v is a group homomorphism, then the image of v is a subgroup of gamma, and so by our earlier remark, the subgroup of this totally ordered abelian group is also a totally ordered abelian group, and this subgroup, the image of phi, it's called the value group of phi. And frequently, instead of working with some random gamma, we just work with the value group. So frequently, without loss of generality, if you want, you may assume for simplicity or convenience that v is simply surjective. That is, just for simplicity, sometimes I'll just assume that the image equals the whole of gamma. Okay, so now on to the characterization of discrete valuation rings. It brings us to our next proposition. Let R be an integral domain with fraction field K, then the following are equivalent which we abbreviate as TFAE. So the first statement is that R is a valuation ring of some valuation on K cross whose value group is isomorphic to Z. Okay. So the second characterization is that, again, R is a valuation ring, but it has this commutative algebraic property that it's Noetherian. So R is a Noetherian valuation ring. Okay. So the next two characterizations will be purely algebraic. So R is a PID with unique maximal ideal. And the fourth characterization is that there exists an element, not necessarily unique, but there exists an element that's non-zero in R, says that every non-zero ideal I equals a power of this element pi for some m larger than or equal to 0. Okay. So I have these four statements, and the proposition is that these four statements are equivalent, and so any ring satisfying one of these four equivalent conditions will be called a discrete valuation ring. So remark, any ring satisfying the above equivalent conditions is called discrete valuation ring, or DVR for short. Okay, and now if you look at the second property, one of the ways in which we can characterize DVRs is that it's a valuation ring with the property that it's Noetherian. And so if you take any valuation ring that's not a DVR, it will turn out to be non-Noetherian. So in essence, what we want is, just for simplicity in a first course in algebraic number theory, we'll always just assume that the value group is Z. So what condition 2 tells us is that if you want to avoid non-Noetherian rings, I guess both condition 1 and 2, what they tell us is that if you want to avoid non-Noetherian rings, then we are forced to consider valuation rings whose value group is isomorphic to Z, and so this is usually a starting point in a first course in algebraic number theory. For the sake of simplicity, in a first course in algebraic number theory, one often just considers discrete valuation rings instead of general valuation rings. But I should say that even the theory of general valuation rings is quite useful. Okay. So now let's go to the proof. So proof of proposition 38. So we have these 4 statements and we want to show that these 4 statements are equivalent. So let's begin with showing that the first statement implies the second statement. And what's the first statement? So we suppose condition 1, which is that R is the valuation ring of a valuation V on K cross with value group isomorphic to Z. And what do we want to show? We want to show that R is a Noetherian valuation ring. Since by hypothesis R is already a valuation ring, it's enough to show that R is Noetherian. That is enough to show R is Noetherian. So let's take an ideal and let's try to show that it's finitely generated. So let I be an ideal in R, and again, let's for simplicity, let's assume that I is not 0. Now since R is a valuation ring, let's unwind what it means. For some valuation V on K with value group. So I said it's isomorphic to Z, but I'm just going to assume for simplicity again that it's just Z. So you just take, so what does it mean for R to be a valuation ring? It's a set of all elements in K cross such that its valuation is larger than the additive identity. The additive identity of Z is just 0. And I'll write the subscript Z to indicate that it's the additive identity of Z along with the 0 element of R. And the maximal ideal is the set of all elements such that the valuation is strictly larger than 0 along with the 0 element. And the units of this ring, these are all elements in K cross with the property that its valuation equals the additive element 0Z. Okay, now we began with this ideal I, and we want to use some property that we want to use a property that the value group is isomorphic to Z. So we want to use some property that we are in Z. So define an element V naught, which is the minimum. So you run over all the elements in I and suppose that X is not 0. Since I is a non-zero ideal, there are elements in I which are not 0. Now consider its valuation. Since every element of I, since I is an ideal of R, every element of I belongs to R, and so its valuation is larger than or equal to 0. Which means that this set of valuations, this is a priori a subgroup of a subset of Z, but since every element of I is in R, is actually a subset of the non-negative integers. Okay, so since you're working with a subset of non-negative integers, such a minimum always exists. Okay, so let V naught be this minimum. So you let X run over all the non-zero elements of I and take the valuation. It's some subset of the non-negative integers, and you take the minimum, call that V naught, and now choose an X naught in I such that its valuation attains this minimum. Okay, and by hypothesis, this element, since you're able to take valuations, this element is not 0. Now you take any element Y that's also in the ideal but that's not 0. Since the element Y is in the ideal I, its valuation should be larger than or equal to V naught by the construction of V naught, and this is just the valuation of X naught. And so now if you just play around with the valuation of Y, so the valuation of Y is nothing but, well, what's Y? It's Y over X naught times X naught. And since V is a group homomorphism, you can write this as the valuation of X naught plus the valuation of Y over X naught. And now, so what we have is that the valuation of Y minus the valuation of X naught equals the valuation of Y over X naught. Okay, but we've just seen that the valuation of Y is larger than or equal to the valuation of X naught. So combining the two observations in the red boxes, what do we get? Since the valuation of Y minus the valuation of X naught is larger than or equal to 0, this implies that the valuation of Y over X naught is also larger than or equal to 0. And now we have this element Y over X naught whose valuation is larger than or equal to 0. So this means that Y over X naught in fact belongs to R. And so what have we shown? This implies that y is y over x naught times x naught. So this first fraction belongs to R. So y is a multiple, a scalar multiple of x naught. So it in fact belongs to the ideal generated by x naught. So what we've shown is that any random non-zero element y of the ideal I since it sits inside the ideal generated by x naught. So we've shown that if you take any element of the ideal I which is not 0, it sits inside the ideal generated by x naught. So I sits inside x naught. The 0 elements belong to all ideals. But x naught by definition belongs to I. We have that the ideal generated by x naught also sits inside I. So combining both the inclusions, we have that the ideal I is this principal ideal generated by x naught. Okay. So in fact thus we've shown that every non-zero ideal is principal and hence R is a PID. And so every ideal of R is generated by one element. In particular, every ideal of R is finitely generated. So in particular, R is Noetherian. And so this proves the implication 1 implies 2. Okay. Okay. Now for the next implication, let's try to show that 2 implies 3. And again, what's the hypothesis? What do we have? Statement 2 is that R is a Noetherian valuation ring. And what do we want to show? We want to show statement 3, which is that R is a PID with unique maximal ideal. Okay, and again, proof of this implication, since R, so by hypothesis R is a Noetherian valuation ring, and so in particular R is a valuation ring. So in particular R is a valuation ring, and so what does that mean? So R, since R is a valuation ring, it's a local ring. And hence R has a unique maximal ideal. So the gist of the proof, or the gist of this implication is that we need to show that R is a PID. Okay, so we need to show essentially that R is a PID. So take an element I of R. Now what, by hypothesis R is Noetherian, which means every ideal of I is finitely generated. Since R is Noetherian, every ideal of R is finitely generated as an R module. And so in particular, Suppose you write I as being generated by A1 up to AN for some elements A1 up to AN in R. Now, what I'll also assume is that we choose N so that now A1 up to AN is a generating set. Now I want to choose the cardinality of the generating set, so I'll just choose N so that the cardinality of the generating set is minimal. Okay, and again, without loss of generality, I'll just assume that I is not 0, and if this cardinality, this minimal n, if n was 1, we are done, since we have shown that I can be generated by one element and hence I is principal. So suppose for the sake of contradiction that this cardinality of a minimal generating set n is larger than equal to 2, and take the first two generators. So let I1 be the ideal generated by A1 and I2 be the ideal generated by A2. And since again by hypothesis R is a valuation ring, it is also what we call the V star ring. This was summarized in lecture 13 as theorem 35. And just unwinding what it means to be a V star ring, it means that you've given me two ideals, so either I1 sits inside I2 or I2 sits inside I1. And again, without loss of generality, one of these two conditions must hold. So just suppose that I1 sits inside I2. I1 is the ideal generated by A1, and what we're saying is that it sits inside the ideal generated by A2. Okay, and in other words, the element A1 which belongs to the ideal generated by A1 actually belongs to the ideal generated by A2 as well. And so you can write A1 as some R times A2 for some element little r in the ring R. And now again, our ideal I was generated by A1, A2, A3, so on up to AN. But now what's A1? By assumption, it's R times A2, and so the ideal generated by I is generated by R A2, A2, A3, so on up to so forth AN. But notice that this first element is just a scalar multiple of A2, but you already have A2 in the generating set. So this ideal is nothing but the ideal generated by A2, A3, so on and so forth up to AN. And hence what we have is that A2, A3 up to AN, this is also a generating set. For I with cardinality n minus 1, and this contradicts the minimality hypothesis on n. So n was amongst all the generating set, n was the cardinality of the n was the smallest cardinality, but we've just produced a new generating set that has cardinality 1 less than n. So this contradicts the minimality hypothesis, the cardinality of the generating set. A1 up to AN. So, an assumption, the hypothesis that we assume for the sake of contradiction was that n is larger than equal to 2, so that is false. So, thus n must be equal to 1, and hence I should just be generated by one element and its principal. Okay. So, we have shown the implication 2 implies 3. We will show the remaining implications in the next lecture. Thank you.